This is 4.1.6 momentum. Momentum is defined as the product of mass and velocity. So the equation describing it is P equals to mv. And momentum is a vector, so it has direction. Momentum can be measured in 2 units, which is the Newton second or the kilogram meters per second. Through Newton's second law, we can relate momentum to force, where force is equal to the rate of change of momentum. So from Newton 2, force is equal to the rate of change This means that if force is not changing, if momentum is not changing, then there is no force on our object. Whether the momentum be 0 or whether the momentum be some arbitrary value, as long as there is no change in momentum, then there is no force on the object. Momentum is one of our quantities that's always conserved. Put a box around that statement. That means that the total momentum before an event is equal to the total momentum after an event. Let's look at collisions next. Start a new page. So in a collision, two things can happen. Either our two objects can stick together and move as if they were one, which is called coalescing, or they don't stick together. In either case, the sum of all momentums before the collision is equal to the sum of momentums after the collision. And as long as you start with that principle, any problem is solvable. So when two objects collide, they either coalesce, which means to stick, or not coalesce. So let's look at a few examples. We'll put before and after. If we label this as A and B, and A and B, In this situation, it does not matter in which direction they're moving or not moving in. We construct the equation in the same way. Which is that MA UA plus MB UB. So the mass times the initial velocity of A plus the mass of B times the initial velocity of B. So momentum of A before plus momentum of B before, whichever direction they may be moving or even not moving. So if one of them is not moving, you just put 0 as their velocity and the momentum becomes 0. That's equal to the mass of A after the event times by the velocity of A plus the mass of B times the final velocity of B. If they were to coalesce, then we start with a similar situation. So we've got MAUA plus MBUB equals 2. But after the collision, if they've stuck together, they're moving as a unit. As a unit, they have a new total mass, which is the sum of both of their masses. MA plus MB. I'll put that in brackets. Multiplied by a velocity. Now they have the same velocity. So when I put V, I'm not going to label as either A or B because it's the same for both of them. Because momentum is a vector, you have to include direction. So if something was moving backwards, make sure you include it as a negative. In the situation where they don't coalesce, a few things can happen. And a few different starting scenarios can happen. So, in order for them to collide in the first place, where they don't coalesce, either B has to be stationary, or B has to be moving slower than A in the same direction. So if they're both moving to the right, A has to be moving faster. Because if B is moving faster in the same direction, then A will never catch up and collide. Or B has to be moving in the opposite direction to A, so towards A. And A is moving towards B. After the collision, a few things can happen. A and B could move in opposite directions to each other. So A could move backwards to the left, B can move forward. A could entirely transfer all of its momentum to B, so A stops and B moves faster. Or C, they both carry on moving in the same direction, but there's a transfer of momentum. So for example, A could move slower after it's collided with B, and B will move faster. In either case, you have to think about what momentums you have before. You have to think about direction and put the values in after, and then evaluate. We can also have explosions. The key for explosions is, before the event, the total momentum was 0. Which means that after the event, the total momentum has to add up to equal to 0. This is before and after is equal to 0. So if we did our before and after diagrams, if we had, say, a rifle Before you shoot a rifle, it has no momentum because the rifle's not moving. After you fired the rifle, the rifle moves backwards, so there's recoil, and the bullet moves forwards. So it's the mass of A times the final velocity of A plus the mass of the B times by the velocity of B. And when you sum them up, you should get 0. One of them will be negative, which will be the rifle because it's moving backwards. Now the rifle has a much, much larger mass than the bullet. So if they have equal magnitude of momentum, the bullet must move with a greater velocity because it has a much smaller mass. But they both have the same momentum. We can look at another example, which is radioactive decay. So if before we have a large nucleus of molybdenum, which is MO, molybdenum decays into technetium via beta decay. And so the technetium has a very small recoil. So again, the momentum before, if it wasn't moving, is 0 is equal to the mass of A times the velocity of A plus the mass of B times the velocity of B.
For the gun, we put a negative outside the MA and VA.
You don't need to put a negative in because the velocity will be a negative number. So you're still summing them up, but when you input the value of velocity, the velocity might be -2, and that will turn that into a negative value. Right, start a new page. Next, we'll look at the impulse of a force. The impulse of a force is just the change of momentum. Now, when you apply a force, the force might not apply completely instantaneously and stop applying. The force can apply for a certain amount of time, causing a change of momentum. So let's assume we have a lorry and we want to stop this lorry. To stop the lorry, we have to change its momentum and make it 0 from some finite value. So we can do this in two ways. Apply a small force on the lorry that's opposite to the direction of its motion over a long period of time, and eventually it will stop. In other words, you press on the brakes lightly and you'll stop eventually. Or you let it roll and friction will eventually stop it after a very long time. Or you apply a very, very big force and you stop it very quickly. E.g., you slam on the brakes and the lorry stops quickly, or you smash into a wall where you stop almost instantly. So we have to think about the impulses of forces, because in certain situations it could be life or death, e.g. in a car accident. You don't want a car to come to rest immediately in a car accident, because that will mean that there's been applied a very big force. You want to make sure that the car stops slowly so that the force that's applied is small, increasing the chance that the passengers survive. So we said that force is equal to delta mv over delta t. Now, mass doesn't change, so we can move it outside of the delta. So F is equal to m delta v over delta t. We know that delta v is just v minus u. So it's m brackets v minus u over delta t. Then we can move delta t to the other side, which gives us F delta t equals to m v minus u. So this is called the impulse, which is equal to the change in momentum. If we graph this, we can have two situations. Force can be constant, applied over some time, or force can change over time. So if we have a constant force applied over some time, our graph looks like this. And the area represents the impulse. So this is constant force. And area equals to impulse. Or we could have a changing force applied over some time. And the area, again, represents the impulse. We'll discuss a few applications of this. So, in a car, the fronts of cars are designed to be a crumple zone. So that means that when a car is in an accident with another car, instead of coming to rest very quickly, the front of the car will bend and change shape and deform to slow down or to increase the amount of time it takes for the car to come to rest. That reduces the force that's applied onto the car and reduces the force experienced by the passengers, helping them survive. Athletes, when they jump, for example, people who do parkour, when they jump from a great height and they land, they bend their knees. If they bend their knees, it takes them a longer time to come to rest when they land on the floor. That reduces the force on their bones and makes sure they don't break their legs. So you can find many, many examples where time is increased in order to reduce the force that's experienced, bringing something to rest. Usually it's to do with safety. And that's the end of 4.1.6.